Okay, so we've been talking about FFT algorithms and how to use FFTs to do convolution, and it kind of brings up a topic we revisit kind of periodically in this class, and that's filter implementations. And really what we're doing is, we spend a lot of time as we go through this class, and particularly in the labs, talking about different ways filters get implemented. We want to put some of that down in one place. We've seen a lot of these topics before. We're basically, we have these characteristics we want our filter implementations, computational efficiency. We might be talking about numerical stability. We might be talking about memory requirements, storage requirements. We might be looking at whether it's possible to do parallel implementations, right? So that's a big deal. So, in terms of parallel implementations, if I can take a given algorithm that processes a gigasample per second and break it into a bunch of parallel processing algorithms that all run at 100 megasamples per second, well, that's the difference between different technologies I have to use to implement the filter, and it might be a whole lot cheaper if I break the algorithm up and can do calculations in parallel. Well, it depends on what the filter structure is, whether I'm able to get away with that. I'm going to start this story off talking about FIR filters. And in some cases, these implementations end up translating into our filter design, so we kind of need to talk through this a little bit ahead of time. And so, when we talk about FIR filters, I'm going to start with the general form, and then we'll get a little more specific and start making some assumptions about the math between the FIR filters. So we talk about a general FIR filter. We're going to talk, we'll say we have M taps or M coefficients. And we saw this in one of the earlier lectures where M, when we talk about FIR filters, is often used to represent the number of filter coefficients as opposed to the filter order. For IIR filters, M is always kind of the order of the numerator, the order of the polynomial. The number of coefficients is one more than the order of the polynomial. So fifth order polynomial, fifth order filter, will have 6 coefficients, and so there's this confusion about how we use M, and you just kind of understand from the context whether M represents the order or the number of coefficients. So if there's any confusion, you gotta make sure you get it straight and don't have things off by 1. So for an M-tap filter, our difference equation, y of n, is just written in terms of the input sample values, right? The x of n values. And so in this case, I have a summation. I'll do k equals 0 to m minus 1 now, right, for my upper limit of b sub k times x of n minus k. So there's my FIR filter. My transfer function for that filter, h of z, real easy. I just take a z transform of it. Every single in here has a delay, so I end up with summation k equals 0 to m minus 1 of b sub k times z to the minus k. There's my transfer function. It's just a polynomial in z. And then if I look at my impulse response, the other way that we've talked about characterizing filters, the impulse response ends up, if I hit this thing with a given impulse, I just see one of these coefficients show up in y of n at every delay of that impulse. And so my impulse response is really easy to calculate, and it's just the filter coefficients. So you've seen this a lot in your labs. We're going to assume we start off at 0. I hit it with an impulse. The first sample out I get is going to be B0. That's where my time origin is when the impulse hits. And then I'm going to see B1, B2, And that just continues on until I get out to B sub m minus 1, and then we're back to zeros, right? That's my finite impulse response. It eventually kind of ends, right? And it goes to perfect zeros. So 3 ways to characterize a generic FIR filter. The difference equation, the transfer function with really just a numerator polynomial. There's no denominator. All the poles in this filter are at z equals 0, right? They're all just delays. Okay, so we say this is an all-zero filter, no real poles that shape the transfer function. And then my impulse response. Okay. Now, when we talk about how we build this thing, how we design the algorithm around FIR filters, well, we have a few solutions already in hand, and they're basically the ones you've coded up. First solution. So if we talk about implementations here, right? Implementations, meaning how I'm going to arrange the calculations, how I'm going to arrange the hardware to do this math, right? We've talked about direct forms, right? And these are basically what you coded up in your lab, right? The direct form 1 and direct form 2. And for an FIR filter, there's no difference between a direct form 1 or a direct form 2. And then the second implementation we just got through talking about has some numerical advantages and sometimes some speed advantages, and that's the DFT, right? So here we could use an overlap and save technique to do this in real time and actually process an incoming sample stream for an FIR filter and come up with an equivalent way to calculate those outputs. And that could be a real option. So the direct form implementations, let me draw a picture of the direct form, and then we'll show a variation on the theme here. So my direct form is often given another name. So there are other ways that we call it. You might see this written as a transversal filter, or sometimes we'll say a tapped delay line, right? It's a tapped delay line. Okay, and that's kind of where this terminology of we said a minute ago, the end taps, running into my own stuff here, end taps for a filter is really the number of taps. Tap delay line, we're just going to form delays of the x of n's, and we form a linear combination of those values to form the output signal y of n. So the block diagram of that thing basically is that direct form picture. So I take x of n in, let me draw it out here, and it's just going to go through a whole bunch of single step delays, z to the minus 1 terms. And I go until I get to all of the memory that I'm required to form the output. So in this branch I have x of n minus 1, x of n minus 2, n minus 3, out to my last term was x of n minus the quantity m minus 1. And then I'm just going to add these guys up, right? And so I can form a linear combination of these guys. I'm going to weight these guys, and these are kind of the taps on the delay line. It's a nice little picture here. And the coefficients here should be exactly these B0, B1, whatever terms now for the pointing up here. For the IR filters, we always talk about the numerator coefficients being B's. For the FIR filters, it's the same. They are the impulse response values. So often when you see these block diagrams, you'll see them written just in terms of h of 0, h of 1, h of 2, h of 3, all the way out to h of m minus 1. An M tap filter, and all of these values have to be added up to, well, yeah, this doesn't continue on. This same series, I end up with summation coming out. Those are plus to form the output signal Y of n. So there's my tap delay line representation. This shouldn't be continuous. There's more summing blocks here in between this branch and this branch. Right? Okay, pretty simple. I have a total of m-1 latches. I have a total of m multiplies by scalar quantities. And I have m-1 additions. So there's kind of a measure of the complexity of this realization. Okay, so there's kind of my generic FIR. So there's nothing too different in that setup. Now, what we're going to do next is we start making a few assumptions about the form of the FIR filters. And so I want to talk about kind of a special case of this thing, and it's a special case that we almost always design around. So we're going to look at an important special case. And almost always, if you look at hardware implementations of FIR filters, they're only going to support this special case. And almost all of our designs are going to be directed toward that special case. Okay, and so if in a lot of applications, sonar, radar, any kind of timing analysis, some audio applications, the signal delay as we go through the filter is something that we want to be able to know, right? If I'm going to do the processing, it turns out that every frequency that goes through a filter has a phase shift associated with it. And it's nice to be able to tie that phase shift back to a time delay, right? So it's nice to be able to predict what the output signal is and how it lines up with your input signal, okay? And so this important special case for the FIR filters is something that we'll be able to do really well in the discrete processing world. And what we're going to look for is filters that have constant delay. And by constant delay, what we're looking at is filters that are, regardless of the input frequency, I see exactly the same time delay no matter what part of the spectrum I'm looking at. And what that means is if I have a complicated waveform that has lots of harmonics associated with it, that once I filter that signal, these edge locations are kind of preserved, right? I'm going to emphasize or de-emphasize each of those harmonics differently, but they're going to end up adding in the correct phase when I reconstruct my output waveform. So these constant delay filters are something that we are able to do for FIR filters only. Okay, and so what we want to do, I think we'll do it on the next little lecture segment, is pin down exactly how we can go about designing a filter that has constant delay. And it's a real restriction on what the filter coefficients are going to look like. And so it ends up kind of modifying this picture in terms of a good structure. This is a generic impulse response. Now I'm going to start looking at filters that have an impulse response that ends up providing that constant delay. And like I said, almost all of our designs are going to be restricted to those cases. So we'll do that in the next lecture segment because I'm close to my 15 minutes here. So.